Okay, welcome everyone. So what we're going to be talking about today is we're coming back to talk about delta H, which is molar heat. And there are so many different delta H's. So there's delta H of vape, and what does vape stand for? Vaporization. Good. There's delta H of COND, which is a stem for what word? Condensation. Condensing. You can have a delta HF, which is for heat of formation or for fusion. There are different types of things that you can have a delta H for. All the delta H is it's your energy change, okay? It's the amount of energy per mole, typically. Usually it's the molar heat. In order to get something to either melt or freeze or boil or condense, so any of the phase changes that you're going through, or you could even have a delta H COMB. Anybody want to guess what that is? COMB. Combustion. Awesome. So you can have a whole bunch of different delta H values, and it's just what process are you going through and how much energy does it take for that particular process to happen. So what we're going to be talking about today is delta HF. In this case, we're going to be talking about fusion. So the particles in the solid phase are so compact, and so when we look at this picture, we see that they're really compact. Are they still moving?
Yes.
Yeah, but they're just vibrating, right? And they're so compact, we say, it starts with a D, we say that the molecules are packed how? Densely. Perfect. So let's write dense. That they're no longer free to move, but rather they just vibrate. Solids do not, what do we say that liquids do that solids don't? Flow. Perfect. They do not flow, nor do they take the what of their container? Shape. Awesome. Okay, so melting point, we've talked about this. It's a temperature which a substance simply changes from what phase to what phase to get it to melt. You're starting as a solid, and then it's switching into a liquid. Now, there's a difference between what you call melting point and normal melting point. Just like when we talked about normal boiling point. Normal is when the atmospheric pressure is equal to, anybody remember an atmosphere is what it is? 1. Very good. 1 atm. Do you remember what it is in millimeters of mercury? 760. Perfect. With the decimal point after that. And the melting point is equal in temperature to. Remember when we did this at the beginning of the year, we said that melting was equal in temperature to what? What would be coming back the other way? Freezing. Very good. The melting point and the freezing point are actually the same temperature. It depends on what the environment is surrounding. So if surrounding it is cooler, then it'll be freezing. If surrounding it is warmer, then it'll be melting. But do you remember what's true of the temperature? The temperature stays the same. It's constant. During the phase change, the temperature is constant. But around it could be warmer, or around it could be cooler. It's just that the actual molecules will have the same temperature while they're phase changing. So, boiling point. The boiling point is the temperature which a substance changes from, well, when you boil something, you're starting as a liquid and it's turning into a gas. Perfect. And so again, here we have this word normal. We can get things to boil and we can get things to melt and freeze and condense at different temperatures. And we'll talk about that when we look at the heating curve and the phase change diagram, actually the phase change diagram. And when we take a look at that, we're going to see that we can get a certain pressure and a certain temperature will cause something to boil, but it may not be the normal boiling point. So normal, again, is when the atmospheric pressure is what, everybody? 1. And how many millimeters of mercury is that? 760. Perfect. The boiling point is equal in temperature to what? What's the opposite of boiling? Condensing. Very good. To the condensing point. Okay. The stronger the attractions between particles, molecules, or ions, what would you say? Would it be easier to separate them or harder to separate them if they have stronger forces? Harder. Makes sense. If you've got a stronger attraction, then it's harder to pull them apart. Ionic solids, so just circle the word ionic, these have strong forces. Do you remember what we called them? It starts with an E, the ionic, the forces in ionic compounds and metallics, we called them? Yep, say it. Electrostatic. Good. Electrostatic forces. And it's due to the positive and the negative interactions. Therefore, ionic solids generally have high or low melting points? High. Very good. Molecular solids have weak forces. So the melting points of those are relatively low. And that's why carbon dioxide is found as a gas, or carbon monoxide, or nitrogen trioxide. Any of those are found as gases at room temperature. So example, we've got a melting point of NaCl. And this is ionic, right? This is an ionic solid salt. And you can see that the value is 801 degrees Celsius for the melting point. if you just switch the first element from sodium to hydrogen, now this is no longer, this is now molecular. This is considered a molecular compound. It's negative 112 degrees Celsius. So this has a really low melting point. This one has a much higher melting point, okay? So based on its IMFs, its intermolecular forces, that's what's going to make a difference between having something in the solid state or the liquid state. It's important to note that not all solids melt. Has anyone ever seen melted wood before? No, okay? So there are some things like wood and cane sugar, they decompose. When you start to heat them, they actually will go through a chemical reaction and decompose. Either you'll get burning, where you're adding, whenever we say burning or combusting, what's the other chemical that's involved in the reaction besides whatever it is? Oxygen. Perfect. You're reacting it with oxygen. And reacting O2 with Cha or Cho always gives you? Co and Ho. So get CO2 and H2O. Perfect. Okay. So these will decompose when heated. When substances melt, though, the particles are still close to one another, but the forces of attraction that held them rigidly together in the solid state have been overcome, and so now the particles can move. And so if we switch this into the liquid phase, we can see that now they're sliding and they're flowing past one another, whereas in the solid state, they're more rigid, and it's just a vibration between those molecules or those atoms. When substances boil, the particles are completely what from one another? Separated. Perfect. They're completely separated from one another. And now the attractions between the molecules are completely overcome. So if we take a look at a picture of that, if we switch into liquid phase, there we go. And if we switch into the gas phase, now there still are IMFs, because remember, even like London forces, where they just come together, they basically are just kind of like touching base and then just moving off. There's a slight attraction, it's very temporary, and then off they go. But really, we've broken all ties, okay? If this container were open, they could all escape and take off as they please. All right, and so that's just showing the difference between those. All right, and last thing. So molar heat of fusion, delta HF. This here, what we're going to talk about is fusion, which I'm going to say right above it, everybody write freezing right above it. Because when they talk about fusion here, they're talking about a liquid turning into a solid, okay? So why do we have melting in parentheses?
Because it's the same temperature.
Yeah, it's the same temperature. Perfect. Okay, let's talk about that for just a second. So this is liquid to solid or solid back to liquid. So I'm doing a double arrow saying that I could be going that way or it can be coming back the other way. We were talking about delta H vape before, specifically talking about the delta H vape for water. And what we had said was water's value is 9.70 kcals per mole, and that was the energy that it took to vaporize water. How do you know that it requires energy, that it takes energy to get water to boil? What do you have to do at home if you want to get water to boil? Add heat. You need a stove, okay? You need something to supply the energy, and so you know that those molecules need to absorb energy in order for the water molecules to boil, okay? Now the opposite is true. If you're trying to get the molecules, instead of separating the molecules, to get the molecules to come back together again, that actually releases energy. That actually gives off energy, and something surrounding it will end up absorbing the energy from the outside. Okay, so that actually gives off energy, and that's called an exothermic process in that case. So, in order to go from liquid to gas, it's 9.7 kcals per mole. So what about going from gas back to liquid? What happened here? Is the number the same? Yes, what's the only difference? The sign. Okay? The amount of energy is actually the same. The only change is energy being absorbed or is energy being lost and released? If it's negative, that means what to you? What does negative mean? Energy is being lost or given off or released. If it's positive, then energy is being gained and absorbed. And you have to supply that. Something needs to be supplied in that case for that to happen. So let's come back to where we were before in talking about the same thing here. Instead of talking about boiling and vaporizing, now we're going to talk about freezing and melting, right? So delta HF is the energy required to either melt or freeze. Okay, it's the same amount of energy for either one. It just depends if it's positive or negative. 1 mole of a substance. Here's a big thing. It takes less energy to convert solid to liquid than liquid to gas, and the question is why. So here's the delta HF for water, and it's 1.44 kcals per mole. Everybody write this down. We said that the delta H vape for water was 9.70 kcals per mole. Someone want to take a guess as to why it is, these are both water, this is water and that's water. Why is it that the fusion is only 1.44 kcals and the vaporization is 9.70? Someone want to try to take a guess at why you think it's still water, why is this one so much higher? Not just a little bit, it's a lot higher. Take a guess.
Can you disregard the forces when you get to a gas phase?
Perfect! When you're going from liquid to gas, what do you have to do to those IMFs? Completely break them apart. Awesome. When you're going from solid to liquid, do those forces still exist? Yes or no? Yeah. Yes. So because those forces still exist, when we're switching from solid into the liquid state, we still have those forces. You're just kind of getting them to separate a tiny bit. That's all that's happening. But when you go to the gas state, you are completely breaking off those forces. All right. And so let's try this problem here. Same thing that we did last time, so I told you that there was one type of math problem, okay? Sometimes depending on the units though, you might be asked for different units, so always do the same thing. Everybody say it with me. Circle what you want, write what you got, throw in a bridge, and cross your units opposite. Okay. Before we start that though, when you look at a problem, I want you to underline the information that you're given, the numbers that you're given, okay? So what numbers stand out here? Do you see a number?
20.0.
The 20.0 grams of salt, perfect, and the 6.8 kcals per mole. Are you given any other numbers?
No.
No, and what are we looking for?
Energy.
Energy, but energy is not a unit, so we want to make sure that we have a unit here. What unit could you do energy? I heard joules, but I want you to take a look in the problem. What are we seeing? Kcals. Perfect. So try to look inside the problem, then you don't have to convert anything. Okay, so we've got kcals. Circle that. And now, if you end with one unit, you want to start with one unit. So would you start with the 6.8 or with the 20?
20.
The 20. Perfect. So 20.0 grams. What is salt? I'm expecting that you know what salt is by now.
NaCl.
NaCl. Awesome. NaCl. Throw in a bridge, cross units opposite. Where do I go from grams?
Grams
To moles. Awesome. And so I need an L chart. Sodium is a 23.0 and chlorine is a 35.5. So we're going to get a 58.5 gram for every 1 mole. Throw in another bridge. I don't want moles, so I cross that opposite. I'm trying to get to kcals. Is there a number that we can use now?
6.8.
The 6.8. Where does that go? On top with the kcal, because what number goes with the mole? 1. Perfect. And you don't have to put the 1 there. So now we're just going to multiply and divide. So we've got 20 times 6.8 divided by 58.5. And I'm getting 2.325. And let's do our sig figs here. 20.0. Zero's with the decimal count. So how many sig figs is that?
3.
3. How about that?
2.
2 and 3.
3.
What's the least number?
2.
2. You always use the least number. So how do I round that to 2 sig figs?
2.3.
2.3, and that's in kcals. Awesome. So that's how much energy that it took. All right, and that's basically it for our delta HF note.